Welcome, everybody. My name is Cliff Petrak. I'm from Chicago's Brother Rice High School. At least not anymore. I'm retired now, but I taught there for 40 years, and we've had a lot of our students come to Eastern, I know. I don't think we have any grads here. Certainly not the girls, because we're an all-boys school. But no, we don't have any Brother Rice alums here, huh? Okay. Well, where shall we begin? Don't slow me down with that calculator. When I was about 17 years old, 1 week away from my 18th birthday, just about ready to start at DePaul University to major in math, I was pretty certain I wanted to teach, but that's about as far as my expectations went at that time. But I got a birthday present, and it was a book called The Trachtenberg Speed System of Basic Mathematics. It had been published in 1960, which was the current time. And I read that book, and I just couldn't believe what I had read. And when I got to the end, I did two things. The first thing I did was to pick my jaw up off the floor, because that's how far it had dropped, in amazement of what I had read. And secondly, I went back to page 1 and started reading through the book again, nice and slowly, trying to really take in a lot of the things that I had learned. Now, since that time, there have been other books written, but that was the start for me. And I know that if I hadn't read that book, I still would have become a math teacher, but I doubt if I would have been in front of you today speaking on speed math. It's become a real passion for me, you might say. I've had a chance to speak in about 17 different states and Canada, and I just enjoy it. So, couple questions or thoughts might come to mind when you see the little logo that I use there. First of all, don't slow me down with that calculator. It sort of sounds as if I'm not too happy about calculators. Not quite true. Calculators serve very important purposes in mathematics, such as finding logarithms or trigonometric values of functions, or finding a very large power of a number. That calculator can really help you out, especially if it's a scientific calculator. But insofar as everyday computations dealing with 2-3-digit numbers, no, they're just too slow. Not only are they too slow, but if they really made us into better math students, think about it. Does that also mean that using an audio book makes us into a better reader? I don't think so. Or how about when we type a letter to a friend of ours on a keyboard? Using that keyboard, does it give us a better handwriting? Nope. Same way with using a calculator. Sometimes it can be convenient, but it doesn't make us into a better math student. So I'm not crazy about the calculator at all insofar as calculations go. But for that matter, I'm also very much against the old-fashioned algorithms that we all grew up with. You see, in 1960, when that Trachtenberg Speed System of Basic Mathematics book came out, I had no idea at the time how big a hit it was going to be overseas. The Europeans and the Asians really picked up on it. And they started to incorporate a lot of the ideas and shortcuts in Trachtenberg's book into their own curriculum and into their own elementary math series. We didn't. What we did instead is we said, oh, look at this other thing that's happening here. A handheld calculator. Hey, isn't that kind of neat? I bet our students would like that. Well, soon we all realized that that was not the answer. But unfortunately, the Europeans and the Asians really moved ahead on this thing. So much so that, I don't know if you're aware of this, but every year in this world, in a different country or a different city, there is a competition held for 8th graders. Each country, if they like, can choose to submit a team of about 10 or 12 8th graders, along with a team of coaches that have prepared them, for a mental math exam. Obviously, it's timed, but you cannot use any scrap paper. Once you put down an answer, you cannot erase it or change anything. Everything has to be done mentally. Now, here's the interesting thing. In the last competition that was held, the team that finished in first place was the team from Singapore. In second place was the team from South Korea. Third place Japan. 4th place, Hong Kong. The first 4-place finishers were all Asian countries. Finally, number 5 was Belgium. 6th was Czechoslovakia. Right behind Czechoslovakia was Slovakia. In 8th place was Switzerland, 9th was Slovenia, and 10th was the Netherlands. Now, of course, you're sitting there saying, well, yeah, wait a second, I didn't hear the US of A, you know. Where did we finish? We finished in 28th place. 28th. Somebody asked me the other day, well, how many teams competed? Well, I don't care if there were 28. I don't care if there were 100. I still wouldn't be happy. In our country, finishing 28th, but here's why it happens. It happens because of what I just told you. These kids from these Asian and some of these European countries are brought up with speed math incorporated into their curriculum in their elementary schools. With our kids, the kids that we submit for the competition, what we do is we try to identify the best students maybe around 8th grade and say, hey, you know, I think you'd be great for that competition. Tell you what, our coaches will work with you for the next 2 years. We'll try to prepare you. And the students do try to learn as best they can for 2 years, but they're up against students that have been learning these shortcut methods from grade 1. So that's the problem. So I don't see any improvement soon, unless you do your homework. Your homework is, as I think most of you are future math teachers, your homework is to make $1 gazillion by going out and writing a complete textbook series for elementary schools incorporating speed math methods. Now, on the other hand, if you're going to fluff off on this homework assignment of yours and you're not going to do it, well, then you're going to have to do the next best thing. And that is, you are going to have to learn as many of these shortcuts as possible, certainly for your own good, which you're going to be able to make use of in the classroom. I guarantee you'll be able to make use of them. But you know, when you first start making use of them in the classroom, if you don't tell the students that these are shortcut methods, they're going to think you're a genius. But after a while, you're not going to be able to keep it into yourself. You're going to have to let it out, and you're going to have to tell your students, hey, here's how I was able to get the answer so quickly. I did this and this and this and this. And they're going to love it. For kids that are above average, for them it's the next level up. It's the level they've been looking for. For the slower kids, it gives them a reason for memorizing their multiplication tables and their other number facts. Because they can learn, once they know that, they can use these shortcut methods to make themselves produce answers quicker than the average student. So let me mention then, before I forget, that at the end of today's session, I've got a handout for everybody, and I've also got one of these coupons for everybody for your CPDUs. So make sure you take one of these and one of these. We don't need the handout, however, in getting through this session right now for this hour. So I'll have them up here, and you can pick them up later. Now, let me also mention quickly that if we had enough time, I would talk about shortcuts in addition, subtraction, fractions, squaring, and multiplication. As you know, I'm just handling squaring and multiplication in this hour. And even there, I have to leave out tons of good stuff. Again, with unlimited amount of time, I would be able to present to you 52 shortcut methods. That's how many I've mastered so far, 52. In your handout, I detail 9 of those 52 methods. So it's a nice starting point for you, but 9 is nowhere near enough. Sooner or later, someplace, you're going to have to learn the rest of them. Now, you can take notes. Feel free to take notes, but I'll just mention that all 52 of my methods are in this book, Don't Slow Me Down with That Calculator, which I wrote. It's a self-published book, so you cannot get it in the bookstore. However, the back of your handout has an order blank here. I sell them for $15. With the postage, it's $18.75. So if anybody wanted to buy a book and had the money with them, I would recommend just paying the $15. I do have receipts for anybody who needs them, and I can take a check. Enough of the commercial. I think it's the best book in the world insofar as shortcut math techniques are concerned. And again, it includes everything that I'm going to talk about, along with everything that, unfortunately, we won't have time for. Now, that having been said, I think we can get started. And, oh, this is good. I'm going to pretty much split the time between squaring and multiplication. And feel free to ask as many questions as you want. Feel free to take notes, although I got to tell you, all 40 of my years in the classroom were on the high school level. I never taught on the elementary level. However, I'm learning what it means to teach on the elementary level because for the past, 5 or 6 years, I've been teaching a course during the summer for students anywhere from grades 3 through 9. They hold it back at the school where I used to teach. And one of the interesting things is when those students come into class, I always ask them the same question at the beginning of class. And after the first session, they get to know the answer pretty well. I say to them, is there anybody here who didn't bring a pen and pencil with them? And when I ask that question with that tone of voice, usually there will be a couple of sheepish hands that go up, and I'll respond with, good job, you're ready for class. And they are, because they're not going to be using pen and pencil to figure out answers. They're going to be using their godculators. Comes with a lifetime battery. Why not? Seriously, though, I mean, sure, you want to take notes with a pen and pencil, but I want to stay away from that pen and pencil as much as possible. Right now, I'm in sort of a teaching situation, so you will see me doing a little bit of writing, but I think I'll also convince you that we really don't need the pen at all, except now and then to write down an answer that we're looking for. We won't need it for calculating the answer. Okay, now, with our little introduction out of the way, let's get moving. Here's why we're here. U.S. lags industrial world in math. American students below average in every category, including in every specific area tested, from geometry and algebra to statistics and computation, whether it's addition, multiplication, squaring, fractions, whatever. We've got to do something about that. So you might say, well, wait a second, what do we mean do something about it? What can we do? Kids don't compute very well, don't calculate very well. They want to run for the calculators. I don't allow them to use it. Well, yeah, okay, fine. You don't allow them to use it. What's happening in the meantime, though? They're not learning. Well, let's think about this a little bit. If we're doing a problem, I don't care if we're trying to add 2 plus 2 or we're doing something far more advanced. What's our objective? Well, everybody's going to say the same thing. Oh, my objective, I want to get the right answer. You're absolutely right. That should be the objective number 1. But we should have 3 more objectives in addition to that one, and here they are. We should also try to get the problem done in a minimum amount of time. We shouldn't be working on a problem all period long unless it's really a tough problem that's going to take the whole period. Let's get through the problem as quickly as possible. And let's try to do that, obviously, with a minimum amount of writing, preferably just the answer. In other words, when I say just the answer, I mean, for example, if we're multiplying 2 numbers, we don't want to write one number under the other and then go through all this multiplication. Because after all, what are you saying to the kids? Or what will you be saying when you get into the classroom with the kids? You're going to say, kids, no calculators in my class. I don't allow that. So what are you telling the kids to do? You're telling them that when they multiply 31 times 33, they got to put the 31 there, the 33 here, draw the line, do the 4 multiplications, add up the columns to get 1,023. We don't want that. We want just the answer. We want them to just write 1023 as the answer. And wouldn't it be nice if they can give this answer, as I just did, orally, without paper and pencil, without even sometimes finding it necessary to see the problem visually in front of them? I'm going to show you how we can do some of that. Now, I speak at a lot of schools, and most of you, I don't think, correct me if I'm wrong, are there any people here who are already associated with a school? Oh, okay. Oh, my mistake. You all look so young. I thought you're all freshmen here at EIU or seniors at best. Oh, okay. Well, if you're at a school already, and if you know your school to have speakers in now and then, and if by the end of the session you kind of think maybe your school might be interested in having me, you might want to take one of these, give it to your principal or head of your math department. Now, I bring that up because in the middle of this little flyer, I happen to have a group of 11 problems. Let me show you what the 11 problems look like. And I posed a question. How much time do you think it would take to get through those 11 problems? Now, most of you, and try to come up with an answer, are probably saying, well, let's see, obviously he doesn't want us to use a calculator. Fine. So the only other answer for you, or for your students, if you don't allow them to use a calculator, is the old-fashioned algorithmic method. The algorithm on multiplication, on squaring, etc. I don't know how long it would take me to get through these. If you want me to just take a wild guess, I don't know, 15 minutes or something like that, I don't know. But, if you master the speed techniques, some of which I will show you today on squaring and multiplication, I know that I can get through all those problems. The last time I did it about a week ago, 54 seconds. Less than a minute for sure. Less than a minute. That means we have to average about 5 seconds per problem. For some of those, I can't do that. I can't do that subtraction problem in 5 seconds. It takes me about 6 or 7. 215 squared, that takes me about 6 or 7 seconds as well. But some of these others, you can come up with the answer just so quickly. And again, I'm going to show you how today. So that should be some pretty good motivation, both for you as well as for your students. Now, if you want to become good at speed math, learn all about speed math, it's going to take a little recipe for success. Let me show you what that recipe looks like. It's a 6-step recipe. First, of course, we have to learn what are these shortcut techniques. When we want to square a number quickly, what's step 1, what's step 2, what's step 3? I'm going to show you some of those today. The others are in my book. Number 2, you're going to have to become well skilled in your arithmetic facts. Now, you people, I'm not worried about you. All math majors in here, 7 plus 8 equals 15, and 8 times 8 is 64, and so forth. But the kids can't come up with all those answers instantaneously like we'd like them to. I've had teachers tell me, and I'm not surprised anymore when they tell me this, they'll say, I don't allow my students to use a calculator, but boy, they just don't know their multiplication tables. They have to think and think and think about the answer. But I just can't make them memorize things. Well, wait a second. Who's running the asylum, first of all? I think if you feel it's important for your kids to know their multiplication tables, that's part of the curriculum, and you're going to insist that they memorize it because it's going to count for part of their grade, even if it means giving oral exams in some of the multiplication tables. However, one of the reasons the kids are reluctant to learn multiplication tables and number facts these days, I think, is because they're sort of upset with you. Because they want to, what they're saying inside of themselves is, hey, look, I got a calculator. I can figure out all these computations that you want me to memorize. I don't have to memorize. I know you don't let me use them in a classroom, but when I'm out of the classroom, hey, look at this. Boy, I do this and this. 2 plus 2. Look at that. It's got a 4 there. Isn't that great? There seems to be no motivation for them to learn. A gentleman in Canada was one of the vendors a few years ago, and he gave me one of these as a gift. I don't sell these, but he does. He's got a website, flashmaster.com. Maybe there's better ones than this around, but this is kind of neat. It sort of lends credence to the idea of if you can't beat them, join them, insofar as the technology is concerned. Kids love technology. Back in my day, we learned by way of flashcards or going home to mom or pop and having them drill us in our multiplication tables. Now, it doesn't seem to work as well. I've used this during the summer with these elementary kids, and they just love it. What happens is you program it first for a time, anywhere from 30 seconds to 3 minutes. I've got 30 seconds right now. And you also choose the operation you want to work with. I've got multiplication right now. And when you hit on, or start rather, the 30 seconds starts winding down. It gives you a problem, 3 times 4, which we think is 12. We punch it in. It gives you another problem, 2 times 5. Now eventually, 7 times 3, let's say we get that wrong. We think it's 20. Well, it's going to put up a question mark, meaning you got the wrong answer. Try it again. I think 7 times 3 is 12. They're saying, no, you dummy, it's 21. Here, we're going to give it to you one more time. Oh, 7, I know what it is now. It's 21. So I learned by that. 3 times 4 is 12, and 7 times 3 is 21. They give me that one again. 2 times 3 is 6. Finally, my 30 seconds is up, and they show that I got 5 right out of 7 for 71%. Of course, I got the same problem wrong twice in a row there. The interesting thing about this is it takes whatever problems you got wrong, and it stores it in its memory. So I can come back to this later and I can just ask the machine to present me with the problems that I've gotten wrong in the past. And again, you can program this to give you addition problems, subtraction, multiplication, or division. I can tell you, I know what the question is, what do they sell for? This guy sells them for $49.95 if he hasn't changed the price. But you can check that out if you're interested. If I was teaching on the elementary level, I think what I would do is I would ask our principal if he could ask the librarian to get 1 or 2 of these for the library and have the kids work on them in the library, maybe during a lunch period or whatever. Or if you have enough money, have one or 2 within the office of the math department whereby you can borrow from them. But anyway, technology may help. Number 3 is basically for adding and subtracting. Good eye movement is very important, but the better a reader we become, the more we improve with that ability. But number 3 isn't going to help us too much with squaring or with multiplication. However, number 4 sure is. Memorization of 2-digit squares, ideally to 30. If you can learn them up beyond 30, that's great. It's going to help you. Not just because you're going to be able to square a 2-digit number more readily, but because it's going to help you with a lot of the shortcuts in multiplication, as I will show you. Now, when we memorize our multiplication tables up through 12, we of course are at the same time learning the first 12 squares of the whole numbers from 1 to 12, the last 3 being, of course, 100, 121, 144. But how many of us can go further? How many of us know that 13 squared is 169, 14 squared 196? We keep going. 225, 256, 289. 361, 400, 441, 484, 529, 576, 625, 676, 729, 784, 841, 900. 961, 1024, I could keep going like that, okay? And by taking the time to memorize those, again, as you'll see later on today when we get into multiplication, it can help me with some of these shortcut methods. We want to get away from using slash marks and the little written carry numbers, especially in addition and subtraction. And of course, we want to get away from calculators and traditional algorithmic methods because they're all too time consuming. And actually, the 2 most important of these 6 are number 1 and number 6. You've really got to practice, but if you do, I guarantee it's going to pay off. If you memorize your squares up through 30, I mean, here they are. That's what they look like. Of course, it doesn't do me any good to tell you that 676 is a perfect square unless I can also tell you 676 is a perfect square of 26. You have to be able to associate it, of course, with the number. Now, let's get into squaring. We'll stay with squaring till about 10:10. Okay. One of the things that you notice in just about every textbook, in the back of the book, there's a table of 2-digit numbers and their squares from 10 up through 99. You know, you wonder what 65 squared is. You go to the back of the book. Oh, there's 65 squared. Or your students do that. One of the ways you can really entertain yourself is do what I did here. I wish I had 3 overhead projectors right now, because what I've got here, I broke them down into tens. The teens, the 20s, the 30s. Here I've got the 40s, 50s, 60s, and 70s, 80s, and 90s. If you really want to see the beauty in math, take a look at some of these. For example, let's take a look at the 50s. And in the 50s, just concentrate on the last 2 digits. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Perfect squares. You say, wow, what a coincidence. I'm sure that never happens anywhere else, does it? Well, wait a second. Let's take a look at the 40s. 0, 81, 64, 49, 36, 25, 16, 9, 4, 1. In the opposite direction. Wow. You look at the 60s and you go, well, no, The 60s. Now, we ran out of them here with the 40s and 50s, didn't we? Yeah, there's no more like that. Wait a second. How about the 90s? 0, 81, 64, 40, etc. Just like the 40s. How about the 70s? You say, well, there's nothing special about the 70s. Look at this. 71 squared ends in 41. 79 squared, 41. 84, 84. 29, 29. 76, 76. Symmetry. And you'll find another one in there the same way. But let me point out something else. You look at the 80s. You say, well, yeah, but look at the 80s, 61, 24, 80. Hey, there's no symmetry there, and they're not perfect squares. Nothing special about the 80s. Oh, no? Take a good look. Although I shouldn't ask you to do that because I took a good look for weeks and months, and it took me a while to figure it out. But let's take the number 81. Last two digits are 61. What's special about 61? Does anybody know? Okay. What's the difference between 50 and 81? 31, right? Does anybody know what the square of 31 is? It's 961. Or, instead of finding the difference between 50 and 81, what about the difference between 81 and 100? You say, well, that's 19. What's 19 squared? 361. You could do that with all of these. Now, that's just the beauty of math being exhibited there. It's not helping us with any shortcuts, but I just wanted to point that out. There's some other things that I could show you if we had time. But I want to get into some of the shortcuts. Now, let's begin with some what I call specific shortcuts. There's general shortcuts, there's specific shortcuts. What is a specialized or specific shortcut? I mean a shortcut which will get you to the answer of some operation more quickly. That's the good news. The bad news is it only works for a very limited number of problems or numbers. For example, there's a shortcut that we can use for the squares of two-digit numbers that end in a 5. 15, 25, 35, 45, all the way up to 95. Now, if you are not allowing your kids to use calculators, and I'm all for you there, but if you're not going to allow them to use calculators, and if they have to multiply 65 times 65, you leave them no choice. This is what you're telling them to do. I guarantee you one thing, kids from Singapore don't do that, or any of those other countries that really beat up on us in that mental competition. In fact, that's not mental competition anyway. That's written. Can't do that in that competition. If we had any of these problems on that mental competition test, here's what we would be expected to do. 4,225, 9,025, 1,225, 7,225, 2,025, 225. I didn't have any of those memorized. I just did them. I actually computed them as I was going through them. Now, at first you say, oh, wow, I'm starting to catch on with this guy. This guy is one of those geniuses. I've seen a few of them on TV. No, I'm afraid not. I'm as dumb as a stick. But that's not so bad, because if I was a genius, and if I did have all these great powers to square 5-digit numbers in my head, and there are some people that can do that, you know what would happen? At the end of the hour, you'd be walking out this door here saying, wow, am I glad I came to listen to this guy. He was really entertaining. Boy, can he do the things with numbers. But all of a sudden, reality would set in, and you'd start to say, well, wait a second, though. I'm no better off than I was when I walked in on him. Sure, he entertained me, but I didn't learn anything. I don't have a brain like his. Guess what? We don't have that situation. You do have a brain like mine, probably a whole lot better. So you can do this too. And I certainly hope when you walk out of the room today, you will never, ever take a 2-digit number ending in 5 and go through this nonsense. Now, the question is, however, what did I do? My suggestion in trying to determine how I came up with the answers quickly is to take all these answers break them up into first half and second half. That's going to give you the clues. Now, that being the case, who's the first person who can raise their hand? You don't have to give me an explanation right now, but who can raise their hand and tell me what the square of this number is? Yes?
2125.
I'm sorry?
2125.
2125? No. Yes?
5625.
5625, she says. Let's see. First of all, we notice that all of them end in 25. That's right. And so 75 squared is also going to end in 25. Now the question is, what about the first half? Well, you'll find that with every one of these, you get the first half of the answer by taking the first digit, like the 6, multiply it times the number that normally follows it in rotation. After a 6 comes a 7. 6 times 7 is 42. Or in the case of 75, what comes after a 7? An 8. 7 times 8, 56. You are correct. And you know, in this little format that we have here, I got to let you know, you're not playing with kids here. We have prizes. You like orange, red, or blue?
Red.
The red?
Yeah.
Okay, there you go. All right. See that? Don't you wish you would have gotten that one right? Yeah. But there may be more for you, so hang on. Okay. Isn't this great? So we have about 9 numbers here. You can get them instantaneously. You saw how fast I was, as fast as I could write them down. So you never want to have to do this. You show this to the kids, especially a kid who's below average. Here's some motivation for memorizing the multiplication tables. Say, hey kid, if you know that 6 times 7 is 42, man, you can find 65 squared just like that. That's all you need, is an understanding and knowledge of your multiplication facts. And then, of course, I always try to give them a little further motivation. I say, hey, you're just learning this today. You know what you do now? You go home tonight, get a hold of Mom and Pop. Say, Pop, I challenge you for $1. I'll let Mom call out a 2-digit number that ends in 5. You can use paper and pencil, Pop, or you can use a calculator. I don't care which one. Mom's going to call out a 2-digit number. I don't know which one it is. Let's see which one of us can call out the correct answer the soonest. The kid's going to beat Pop every time if he uses paper and pencil. Or worse still, I'm going to use my calculator here. Here, let's see. Take the cover off, hit the on button, hit the whatever we're doing, 6, and then the 5, and either use the exponent or use multiplication times 6, 5, whichever way you want to do it. And not only that, but then Pop finally gets an answer, and if we wanted to write it down, now he still has to put the calculator down. He has to pick up his pen. He has to go over and write down the answer. Oh my goodness, that's the Middle Ages type of calculations. Now, I know what you're asking. You're saying, hey, I like that. I like that. Give me more. And I know what you're probably thinking. You're saying, hey, that's fine for a number that ends in 5, but gee, what would you do if you had numbers that began with a 5? What would you do then? Well, if you had, and of course, we've only got about 10 of them, don't we? So again, it's a specialized method. It's a great method, but it only works for about 10 numbers. But if you want to take the squares of any of these numbers, just write them down. 2,916, 2,601, 3,249, 3,481, 2,809, 3,364. Okay, how did I get that? Again, my suggestion is split the number down into 2 parts. And that's going to give you the little technique. The little technique that the kids from Singapore use, and Korea and Japan and Hong Kong and Belgium and Czechoslovakia. Maybe not the kids from the U.S., or maybe they do use them, but maybe they don't come up with the answer quite as quickly. Anybody want to venture a try? Oh, I'm sorry, I didn't even ask a number. Let's try, how about, let's go with 56 squared. What would 56 squared be? She says 31, 36. Let's see if she's right. First of all, she notices that with all these others, the last two digits are the square of the units digit. 4 squared is 16. 1 squared is 0, 1. If it's a single digit, you have to put a 0 in front of it. So she says, well, 6 squared then would be 36. Then the question is, how did she get the first half? And you got the first half by?
5 times 5 is 25 plus 6 is 31.
That's exactly right. Of course, since this only works for numbers that begin with a 5, you could actually even make the explanation shorter by just saying, take 25 and add it to the number next door. So 25 added to 4, 25 added to 1, 25 added to 6 gives us the 31. Okay? Blue or orange?
Orange.
Alrighty, very good. Okay, now, at this point, being defined teachers that you are, I'm sure a lot of people are asking you this question, and this is an excellent question. You're saying, yeah, it's a real nice shortcut, but is this a magic trick? I mean, how do we know it's always going to work? You can test out the 10 problems or so, but is that really a way of proving this? Here's how we prove it. With either of those two methods that I've shown you now, for numbers that end in a 5 or begin with a 5. The proof would look something like this. It doesn't require any more knowledge than what you would have or learn in an Algebra 1 course. Let's just take the numbers that end in 5. Any two-digit number ending in 5 could be written as 10t plus 5. When you square that binomial, we get this trinomial. If you take the first two terms, factor out 100t, we get 100t times t plus 1 plus 25. Let's use our commutative property, flip this around a little bit, and we get t times t plus 1 times 100 plus 25. In other words, what we're learning here is that the square of any two-digit number will always equal the tens digit, like here's an example with the 85, the tens digit 8, times t plus 1, that's 8 plus 1 or 9, 8 times 9, that's 72, times 100, 7,200, plus 25 every time. So 7,225. And you've got a similar type of derivation here, or proof, for a number that begins with a 5. Of course, I know what you're saying. You're saying, you're making yourself look good here with these numbers that begin or end with a 5. How about a real tough one? How about something that begins with a 9? Yeah, now there's a tough one. How would you do that, huh? Okay, the situation is just a tiny bit different. Here's what we do. Once again, there's going to be a first half and a second half to the problem. Here's what you do. It takes a little preliminary step. The preliminary step, which you can do in your head, of course, subtract the given number. Let's take 97. Subtract a number from 100. Okay, it's 3, right? I wouldn't normally write this down, but just so we can sort of see it. It's the first time perhaps you are seeing it, so that's why I write it down. So you take that little number, which represents the difference between the number and 100. Now, to get the first half of the answer, subtract that little number 3 from the given number. 3 from 97, 94. That's easy, isn't it? And the second thing we do is we take that little number and we square it. 3 squared is 9, which we write as 0.9. We're finished. That's pretty nice. For a blue bag, what would it be for 99? Got to raise your hand so I know. Yes?
10,081.
10,081. No.
9,000.
Yes.
9,501.
9,501. No.
9801.
She says 9801. Let's see. The difference between the given number and 100 is 1. We do two things with the 1, like we did over here. The first thing we do with the 1 is we subtract it from the given number. 1 from 99 is 98. The second thing we do with the 1 is square it. 0, 1. 9,801. You are left holding the bag. Can you catch it? Thank you. And all of a sudden, the prizes are deteriorating rather quickly. Okay. Once again, with the 96, the little number would be a 4. So we subtract 4 from 96, and then we square the 4. Okay? Now, to stay on time, I'm going to have to skip the 80s, but I can tell you that there's a shortcut method for squaring numbers in the 80s, in the 70s, in the 60s, in the 30s. There's no shortcut for squaring numbers in the 20s or in the teens, and that is why I told you a little bit earlier that one of the requirements for speed math is that you should, for sure, memorize the squares of two-digit numbers up to 30. Because beyond 30, there's a shortcut method for every one of them, depending on what decade they fall in. Now, some people might say this: oh, are you telling me that, okay, fine, I'm going to memorize the two-digit squares up to 30, and you're telling me I'm going to have to learn this method for numbers in the 30s and another one for the 40s, 50s, 60s, 70s, 80s, 90s. That's an awful lot for me to memorize. First of all, it's fun. You're going to want to do it. But let me take your side. You say, hey, that's too much to memorize. Okay, fine. Then let's not do a specific or a specialized method of squaring. Let's instead look at a generalized method, a method that will work for every single two-digit number, whether that number is 10 or whether it's 99. And it looks like this. Just 3 steps. We square the units digit. Secondly, we multiply the tens digit times the units digit times 2. And finally, we square the tens digit. Now, if we relate that to a specific example, it'll become very clear. Let's pick a number. Let's do an easy one first. Let's pick 43. We want to square 43. Now, when we finish with step 1, we're going to have the digit of the answer that's furthest to the right. In other words, the units digit. Here's what I mean. Square the units digit. Well, here's the units digit, 3. 3 squared is 9. That's going to be the far right digit. Next, multiply the tens digit times the units digit times 2. 4 times 3 is 12, times 2 is 24. 24, right down to 4, carry the 2. Last step, square the tens digit. When I square the 4, I get 16, and the 2 I carry is 18. 1849. I'm finished. Incidentally, before I do another example of this, at the end of the second step, I had to carry a 2. And I don't know if you noticed me. I said, what was it, 24. I said we write down a 4 and carry a 2. I did this. That was not by accident. I told you I was dumb as a stick, and I'll prove it right now. I have trouble remembering what I'm carrying, okay? Now, I don't believe in adding on my fingers, but I think it's very convenient that we all have 5 fingers on each hand because they can help us to remember a particular digit that we're carrying. And here's what I mean. Anytime I want to remember 1, I do this, or a 2, or a 3, or a 4, or a 5. That's obvious. Now, to remember 6, I don't want to do this because I might need this hand for another digit later on. So I'd like to be able to remember a 6, 7, 8, 9, or 0 on the same hand. So what I do is, once we get beyond 5, when I want to remember a 6, I do this. I touch the thumb to the forefinger. That's my 6. A 7 is to the middle finger. An 8 is to the ring finger. A 9 is for the, a 9 would be touching the thumb to the little finger. And if I want to remember a 0, I use a closed fist. I don't use this for 0 because that would be my 6. And there's always somebody who seems to remind me, hey, wait a second, you got it backwards. And I say, what are you talking about, have it backwards? They say, do you know sign language? I say, no. And somebody told me a long time ago, they say in sign language, I guess, this is a 6. It's the very opposite of what I came up with. I just came up with this on my own. But they use this for a 6, this for a 7, this for an 8, this for a 9. I don't even know what they use for a 0. But, oh, what is it?
This is 10.
Yeah, but what if it's just a 0, not a 10? Aha! You're going to have to work on that. I'd love to know the answer to that. And then we've got the other hand to remember another digit. So in this problem, I had to carry a 2, so I did this. But if I had to carry, let's say, an 8, I would do this. And then later, I'd take a look. Oh, and I'm carrying an 8. Okay, and I I would add it on. Let's do a tough one. Let's do, hey, I tell you what, let's do the toughest one possible. Let's do 99. Now, before we even do 99, you're going to be presented with a choice to make pretty soon. As soon as you get this method down, the next time you have to square 99, you're going to say, wait a second now, wait a second. He showed me a specialized method for squaring a number that begins with a 9. You know how it's done, right? You got the 99 right. But on the other hand, you're going to say to yourself, well, on the other hand, he also showed me a 3-step method whereby I can square any 2-digit number, including 99. Which one of those two should I use to determine what the square of 99 is? The answer is use whichever method you feel you can come up with more quickly. I think in the case of 99, though, we'd all agree when you're finished seeing this, that'll be the method that you just learned a little while ago. But let's suppose we didn't know that method. We're relying strictly on the generalized method. Here we go. 9 squared is 81. Write down to 1, carry the 8. Second step, multiply the tens digit times the units digit times 2. Oh, and incidentally, she's speaking at another session. I mentioned that to you because I don't want to see a mad rush of people going out the door, you see. She told me that she was going to have to leave. Anyway, okay, so step 2, we multiply the tens digit times the units digit, 81, and we double 81. We have to do that in our heads, 81 times 2, or 81 plus 81, whichever way you want to think of it, 162. 162, but we're carrying 8, that's 170. There's the 0, and I have to carry the 17, carrying 17. Last step, square the tens digit. 9 squared is 81, and we're carrying 17. 81 plus 10 plus 7 is 98. A lot of work, but that's a tough problem. Okay, but that's the way you square any 2-digit number. So if we just did one more, let's do 57, and you know how to do that one already too, because it begins with a 5. But if you didn't know that method, we'd say 7 squared is 49. Write down to 9, carry a 4. Multiply 5 times 7 times 2. That's 35 doubled is 70, and the 4 we carry is 74. Carry a 7. Last step, 5 squared is 25. 25 plus the 7 is 32, and we're finished. Okay? Any questions about that method? Okay. Oh, wow, we got to go. In doing squaring and multiplication, I'm leaving out squaring 3-digit numbers. Yes, there is a method. It involves 5 steps. And for those of you who are real eager beavers, yes, there's a method for 4-digit squaring as well, okay? 7 steps. I'm not trying to tell you that if you use this method on a 4-digit square that you're going to get the answer faster than you would with a calculator. No, you wouldn't. Fortunately, we don't have to square 4-digit numbers all that often. But I will tell you this, once you learn this method, you'll be able to square a 4-digit number faster than if you were to take 2,132 and stick it under each other, you know, with the line and all the numbers. We don't want to do all those numbers anymore. Okay, let's do a little something on multiplication. Recently, there was a news article about 3 schools in New Jersey that were at odds with each other because the superintendent's office found out that the 3 schools under his jurisdiction were all using different math textbook series. And so he went to them and he says, I want the 3 of you schools to get together and just pick one of your math book series to go with. We don't want 3 different math book series in our district. Well, the 3 schools couldn't get together. They were very adamant about the particular math books that they were using. Well, the reporter says the reason they were so adamant is because each one of them really loved the way computation was taught in their textbook. This is what they had. The first school used a textbook series that taught multiplication this way, which basically is the way I learned way back when. It works. The chances are most of you learned using that method, but I don't like it anymore. I think it's too slow. Too much writing also. The second school used this method. Same problem. They want to make sure the kids understand where all these numbers come from. So they said, well, 12 times 25, that takes in 20 times 10, which is 200, 20 times 2, which is 40, 10 times 5, which is 50, and 5 times 2, which is 10. We add those up, we'll get 300. They're telling their students every single time you multiply a pair of two-digit numbers together, we want to see all these numbers written here. Think that's what the kids from Singapore do in this case? I don't think so. Well, I was really getting annoyed watching this, and I thought to myself, what in the world are they teaching these kids? It's taking them so long to get to answers. And I thought, what in the world could the third method be? Well, the third method threw me. I had never seen the third method before, and I hope I never see it again. It looks like this. It's called matrix multiplication, as perhaps some of you know. There's the 12 up there, the 25 here. 2 times 2 is 0,4. 2 times 1 is 0,2. 5 times 2 is 1,0. 5 times 1 is 0,5. You have all these lines, and some teachers might require that you use different colored Crayola for each line, and positively use the ruler, of course. And so you finally, you add up these numbers. There's a 0. This is 10. Carry a 1. 2 plus 1 is 3, and 0. So there's your answer, 300. So all of our scientists and engineers, this is the way they multiply 12 times 25. That's what the kids are told. You do this every time you're multiplying 12 times 25 or any pair of two-digit numbers. In the meantime, I'm looking at the TV screen and I'm saying, where is my method? Here's my method. You just put down the answer. Now, I don't want you to say, oh, sure, 12 times 25. You see, 25 fits into 104 times, and 4 goes into 12 3 times 100 or whatever. No, it's got nothing to do with the actual numbers of 12 or 25. We can multiply 12 times 25 or any pair of two-digit numbers quickly with a general method. Here's the general method. It looks a little bit like the method for squaring a two-digit number, but after all, it should, because when we square a two-digit number, we are multiplying a pair of two-digit numbers. So here's the way it works. Let's suppose we had 52 times 83. Step 1, multiply the units digits. So we multiply 2 times 3 to get 6. Second step, find the sum of the cross products. That means, here's our cross product, 16 and 15. 16 and 15, that's not too tough. 15 and 15 is 30, plus 1 more is 31. Write down to 1, carry the 3. Last step, multiply the tens digits. 5 times 8, 40, and the 3 we carry is 43. We're finished. Or would you rather 52 times 83? 3 times 2 is 6. 3 times 5, oh my goodness. I haven't done this in a long time. I'll probably make a mistake here, but no, I got through it. I don't multiply that way anymore. We just want to write down the answer. And granted, you may have a couple of problems where the numbers are rather large. I mean, you could have something like 69 times 97, let's say. Okay, it's going to take us a little bit longer, especially that middle step. But we can get through it, can't we? 9 times 7, 63. Write down to 3, carry the 6. Kind of important. Now, I could do this. I could put down a 6 off on the side here someplace. I don't want to do that. Each time I make a mark on my paper, it's taking time. I want to save that time. So this is easy. I don't have to write anything down. Here's my 6. Okay. I've got cross products of 81 and 43. 6 times 7, 42. 81 and 42. Well, 80 and 40, it's 120. 120 plus, 3 is 123. 123 plus the 6 I carry is 129. Write down to 9, carry the 1, 2. Carry the 1, 2. Last step, multiply the tens digit. 6 times 9, 54. 54 and 12. That shouldn't be too tough. If it is, take the 12, break it down into 10 plus 2. Okay, so 54, 64 plus 2 more is 66. 6,693. Isn't that nice? Keep doing that and teaching that to your kids. Pretty soon they're going to be challenging those kids from Singapore and Japan and Hong Kong and the rest of them. Now, of course, I know what you're asking. You're asking whether there is a similar process for multiplying, let's say, a pair of three-digit numbers. We're not going to have time, but it looks like this. You take your 3 numbers, it's 5 steps, you're going to multiply the units digits, Then you're going to take the sum of the cross products here, and then this is the toughest step. It's going to be the corner products plus the middle, the tens product. And then step 4 is the opposite of step 2. Step 5 is the opposite of step 1. It reminds you again of climbing up a mountain. And when you get to the peak, that's the toughest step, the third one. And steps 4 and 5 are much easier. And again, looks a little bit more like a football play than mental calculation. But yeah, there's a 7-step method here. 1, 2, 3, 4, 5, 6, 7 steps if you want to multiply a pair of 4-digit numbers. But again, that's more advanced stuff. Well, I don't care if you're a teacher or a student. That's the kind of stuff you leave toward the end. First, you have to get the computations down that involve a pair of 2-digit numbers. What do we have, 5 minutes? 10:30 is it? Okay. Let me teach you a specialized method for the 2-digit numbers. I think one of the most useful ones, you know how many times we have to multiply numbers that are in their teens, numbers that begin with a 1? Now, you can use the general method, and the general method is pretty easy, of course, but there's an even easier way. You know that for 13 times 15, it's going to involve 4 multiplications, 10 times 10, 10 times 3, 10 times 5, and 3 times 5. If I am doing this problem of 13 times 15, I'll let you hear what I am saying to myself as I do this problem. I say to myself, in fact, I'll write it down. I say to myself, 100, 130, 180, 195. In other words, I multiply these two numbers. That's step 1. It's always going to give me 100. I am going to then add the product of 10 times the first digit and then 10 times the second digit. So when I look at this, I think 30 because 3 times 10 is going to give me 30. When I look at the 5, I think of 50 because 5 times 10 is going to give me 50. So 100, 130 plus 50 gives me 180 plus 15 is 195. Or I'm going to say 100, 170, 250, 250 and 56. 250 and 56, 306. Over here, 100, 190, 230, 230 and 36 is 266. Now, if the numbers are presented horizontally, okay, you got 100, 160, 180, 192. Now this one, we're almost out of time. I've got to show you another specialized method. If you're multiplying two numbers that differ by just one integer between, like 17 and 19, we know it's 18, right? All you have to do, take that middle integer, and assuming you know it's square, if you don't know it's square, it's not going to help you. But if you know it's square, if you know what 18 squared is, 324, all you have to do, subtract 1, 323. Does it work for 13 times 15? You bet it does, because the middle number is 14. 14 squared is 196. Subtract 1, 195. Works like a charm. So we can use that. That's called teen multiplication. And we got 2 minutes. You can also do it in reverse. If you want to multiply any pair of 2-digit numbers that end in a 1, like 61 times 21, 60 times 20, that's 1,200. 1,260, 1,280, and it's always going to end in a 1. 1,281. 300 times 700, 2,100, 2,130, 2,200, 2,201. 80 times 40, 3,200, 3,280, 3,320, and it ends in a 1. So it's a great shortcut there. I wish we had another 2 hours or so. We could lock the door on Joe Ellen and stay here longer. We could send out for pizzas, whatever you want. I have all sorts of material that could keep us going all night. The one thing is, if you really are interested, they're all in the book if you care to buy a book. Otherwise, I'm repeating this session in about 5 minutes, but I'll be covering most of the same material. When I get to about this point, maybe I'll do a few different types of specialized methods for squaring or for multiplication, but other than that, it'll basically be the same. So I hope as teachers you go out there and teach the kids the speed math so we can finish a little higher than 28th place the next time. Okay, now don't forget as you're leaving, take a copy of a handout, and anybody who might want to buy the book through the mail, again, you got the application on the back. Otherwise, I've got copies here, and if you think your school might be interested in having a speaker, take one of these. Especially if you think the speaker would be me. But other than that, you guys were a great audience. Thanks for coming. You were really